Chapter 7, and it's got some interesting cool stuff. The first thing is there are magnetic properties of different elements. They are a function of the electron arrangements. So however the electrons are arranged in an atom will affect its magnetic properties. And what is the magnetic property? Remember, we talked about electrons are negative and they're spinning. So as they spin, they create a magnetic field, or they're affected by a magnetic field. So how can they be affected? Well, you have two options. You have paramagnetic, which if you have a sample that's placed next to a magnet, it's attracted to the magnet. Okay, if it's diamagnetic, then you put it near the magnet, it's repelled by the magnet. So we can look at this and see whether something is attracted or repelled by the magnet. Okay, so a paramagnetic is a weak attraction to a magnetic field. Now the question is why? It's attracted due to electrons unpaired. So when you put in electrons into degenerate orbitals or into any orbitals, for example, in the case of silver, you have an unpaired electron here. So that means it's going to be paramagnetic. Now, diamagnetic, remember, is a weak repulsion to the magnetic field. And this time, it's due to all the electrons are paired. When they're paired, they repel. So if you'll notice, we have no unpaired electrons here. Therefore, zinc is going to be diamagnetic. Now, and you're thinking, wait, some things are really good magnets. Yes, they are. And we call these ferromagnetic, and they are exceptionally attracted to a magnetic field, which we set up here for the paramagnetic. But here with the electrons unpaired, it's usually like one or two. Okay, down here we have multiple electrons that are unpaired. Okay, so if we look at iron, we have 1, 2, 3, 4. So most magnets deal with the simple ones. You can actually take something that's iron and rub it against a magnet and make it magnetic. It's the easiest one. It has a set of 4 unpaired electrons, so therefore it makes it really magnetic. So the question is how do you do this? Well, again, you need a periodic table. So cobalt happens to have 27 electrons, but when we look at it, we want to use the noble gas configuration. So cobalt is equal to argon. So 1, 2, 3, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. 7. Okay. Now, there's my configuration there for the cobalt. Let's look at cobalt 2 plus and cobalt 3 plus. Now, I'm going to actually erase this, and this is the beauty of color coding. So I'll do cobalt 2 plus in blue. So if I'm 2 plus, I can lose electrons either in the D or the S. So let's go back real quick and look briefly here. And I know I told you that the boxes are bad, but here it's easier to see. Here's my 4S, here my 3D. So I have my 2 in my S, 1, 2, 3, 4, 5, 6, 7. So if you look at it this way, and we're going to lose 2. The best place to lose them are going to be in the D's, because that means, using the same methodology here, I have the pair here, but now I went to 2 more unpaired. Well, it gets even more interesting if we go to cobalt 3+, because then we'll lose an S. We're not going to lose another whoops, I wrote that in there. We're not going to lose another D, because it's half filled. So we'll have 3S1, 3D5, which means when we look here, 2, 3, 4, 5. So we have 1, 1, 2, 3, 4, 5. So now we have that many. Okay, so then this begs the question of how many unpaired electrons do I have? In cobalt I have 3, in 2+, I have moved to 5, and in cobalt 3+, I've moved to 6. So think about it. The more unpaired electrons, the better you are in terms of the ferromagnetic. Okay, so this would be a good magnet, this would be a better magnet, and this would be a great magnet if you're making it into the compounds. So, looking at this, are the following paramagnetic? Well, this one's going to be para. If you don't have a choice, it's going to be para. Of the para, it would be ferro, because it has multiples. Okay, yttrium, if you look at it, it's going to have the core, and then it's going to have 1, 2, 3, 4, 5. 2, 3, 4. So it's krypton, I think. I don't have my periodic table. Yeah, it's krypton. So it's 1, 2, 3, 4, 5s2. So 5. 4d1. So it has an unpaired, so it'll be paramagnetic. Barium is going to have a xenon core, and it's going to be 1, 2, 3, 4, 5, 6s2. It has no unpaired electrons, so it's going to be diamagnetic. So if you haven't figured it out, you can look at the ends of filling shells that are full, and they're all going to be paired, so they are not going to be paramagnetic, they're going to be diamagnetic. So this is an easy trend, but it's real simple to look at it and go, are we para or are we diamagnetic? Okay. Now, you can read through these sections and look at the trends associated with other processes. These are all group 1, lithium through potassium and sodium. If you drop lithium onto water, it just kind of bubbles. It's forming hydrogen gas from the water. It's not real impressive. If you notice this, we have flames here. Okay, if with potassium you have flames, and I say dancing, because it keeps moving. The little piece of potassium actually bounces around the surface, so they're going to react differently based upon their family. Same thing for the halogens. Chlorine strictly a gas, bromine is a liquid, and iodide is a solid. And sulfur, remember back we said that there was a form that was S8, and it's because of its electronic properties. So that ends chapter 7, and so you'll have that on the test as well.